We are going to discuss about the orientation and reactivity of E2. So second order dehydrohalogenation proceeds by the E2 mechanism. So if substrate contains more than one type of beta hydrogen, more than one product will be formed. So look at the first reaction. So here RCH2, CH2X. So the first carbon is alpha carbon and the second one is beta carbon. So here only one beta hydrogen is available. So only one product RCH double bond CH2. Then in the second reaction, it should contain two beta hydrogens. So there are two elimination products RCH double bond CH3 plus RCH2 CH double bond CH2. So it has been observed that in such cases one of the alkene is formed as major product and the other one as the minor product. So second order dehydrohalogenation proceeds by E2 mechanism, and dehydrohalogenation often yield a mixture of isomeric alkenes. So let us consider elimination reaction of butane, bromobutane in presence of alcoholic KOH. We can get 2-butene as the major product. It should contain about 81% or 80 to 81% of 2-butene plus 90 or 20% of 1-butene. 19 to 20% of 1-butene. So here 2-butene is the major product and 1-butene is the minor product. So next, bromopentane. Likewise, bromopentane on alcoholic hydrolysis, we can get 2-pentene 71% and 29% of 1-pentene. So in order to decide which of the isomeric alkene will be obtained as major product, Satis formulated a rule known as Satis rule for elimination. So here methyl bromopropane in presence of alcoholic KOH, we can get 72% of major product and 28% of minor product. So in order to decide which of the isomeric alkene will be obtained as major product, there is one rule. That rule is called as Satis rule, which is introduced by the scientist Satis. So in an elimination reaction, the more substituted alkene is obtained as the major product. So next is the justification of Satis rule. So two major factors contribute to this are the stability of the alkene and the lower energy of activation. So first one is the stability of the alkene. So as the number of alkyl substituent attached to the double bonded carbon increases, the stability of the alkene increases. And the stability of the alkene is measured in terms of the heat liberated when the double bond undergoes addition of hydrogen, that is heat of hydrogenation. The lower the heat of hydrogenation, higher is the stability of alkene. So in this one, which one is more stable? So the first one, which is having a heat of hydrogenation of 30.3 kilocalorie, and the second one, that is 2 butene, which is having cis isomer of 2-butene, which is having a heat of hydrogenation of 28.6 kilocalorie, and trans isomer of 2-butene, which is having a heat of hydrogenation of 27.6 kilocalorie. So lower the heat of hydrogenation, higher is the stability of alkene. So here trans butene is 2-butene is more stable than the cis and the cis isomer. Okay. So as the order of substitution of double bond increases, the stability of the alkene also increases. With increase in the order of substitution, the number of R substituent attached to the double bonded carbon atom increases. This increases the inductive effect, positive inductive effect, and the number of hyperconjugative structures also increases. Then second one, lower energy of activation. So here in the transition state, the double bond is look at the transition state. Here the double bond is partially formed between C alpha and C beta. That is, the transition state has considerable alkene character. So as the number of R substituent attached to the C alpha and C beta carbon increases, the energy of the transition state goes on decreasing. That is, energy of activation required to form transition state decreases. Hence, more substituted alkene is formed at faster rate. So thus the more substituted alkene is obtained as major product because it is more stable and formed as faster rate due to less energy of activation. So here 1-butene is the minor product which is having higher activation energy, and here 2-butene which is having the lower activation energy. So here 2-butene is the major product. So if activation energy decreases, more substituted alkene is formed at faster rate because it is more stable and formed at faster rate due to less energy of activation. The next one, Hofmann elimination. So in case of some E2 elimination reaction, instead of formation of more substituted alkene as major product, we get formation of less substituted product as major product. Such elimination reaction is known as Hofmann reaction. So whether a given elimination reaction will follow the Seitz's rule or Hofmann rule depend upon the nature of leaving group and nature of the base used. So the nature of the leaving group, consider the following elimination reaction. So first one is the Seitz's product and second one is the Hofmann product. So ഇപ്പോൾ ബ്രോമിനാണ് ലീവിങ് ഗ്രൂപ്പ് എങ്കിൽ 80% നമുക്ക് സേറ്റിസ് പ്രൊഡക്റ്റ് ആയിരിക്കും കിട്ടുക. ഹോഫ്മാൻ പ്രൊഡക്റ്റ് 20% ആയിരിക്കും. ഓക്കെ, സോ അതേപോലെ ലീവിങ് ഗ്രൂപ്പിനെ ഡിപ്പെൻഡ് ചെയ്തിട്ട് നമുക്ക് കിട്ടുന്ന പ്രൊഡക്റ്റിൻ്റെ പെർസെൻറ്റേജും ഡിഫറെൻ്റ് ആയിരിക്കും. So these results indicate that as the size of the leaving group increases, percentage of Hofmann product increases. So ഇവിടെ നോക്കിയേ, നമുക്ക് സൈസ് കൂടുന്ന ലീവിങ് ഗ്രൂപ്പിൻ്റെ സൈസ് കൂടുന്നതിനനുസരിച്ച് ഇപ്പോൾ ട്രൈമീഥൈൽ അമോണിയം സോൾട്ട് അതേപോലെ ട്രൈമീഥൈൽ സൾഫോണിയം ഒക്കെ ആണെന്നുണ്ടെങ്കിൽ, ലീവിങ് ഗ്രൂപ്പ് ആണെന്നുണ്ടെങ്കിൽ അതിനനുസരിച്ച് ഹോഫ്മാൻ പ്രൊഡക്റ്റ് ഇൻക്രീസ് ചെയ്യും, സേറ്റിസ് പ്രൊഡക്റ്റ് ഡിക്രീസ് ചെയ്യും. The nature of base used. So നമ്മൾ 2-bromopentene എടുക്കുകയാണെന്നുണ്ടെങ്കിൽ നമുക്ക് കിട്ടുന്ന പ്രൊഡക്റ്റ് ഏതൊക്കെയാണ്? 2-pentene plus 1-pentene. So here 2-pentene is the Seitz's product and 1-pentene is the Hofmann product. So as the size of attacking base increases, the transition state for the Seitz's elimination become more crowded than the Hofmann elimination, and hence less substituted alkene is obtained as major product.